Hello. In this video, I'm going to explain problem 15 from the 2013 F equals MA contest. In this problem, we have a uniform rod partially submerged in water with one end fixed to a pivot, and we're given the density of the rod relative to that of water, and we're asked to find what fraction of the rod is above the water at equilibrium. I find this to be a pretty interesting problem because it turns out that we're actually going to use both torque and buoyancy, and really meaning Archimedes' principle. And I rarely see a problem that combines these two, so I think this is pretty interesting. So the motivation to use torque is just because of the fact that there's a pivot in the problem, and the motivation for buoyancy is, of course, just the fact that, submerged in water. So let us set up this problem. So we have a uniform rod. Now, you may be able to figure out from the problem statement that you probably should be assuming that the rod is sort of a thin rod, which of course the diagram doesn't show that very well, but you should assume that this is a very thin rod. So let's just draw it something like this. This is the pivot point. Now, I'm going to call this horizontal distance L for convenience. Ultimately, it won't matter because you probably guess it'll probably just cancel out of all of the equations, but I'm just going to label it for convenience. Now, this fraction, so I'm going to say F is what we want. So that's a fraction of the rod above the water. So this fraction right here is F times L. Now, where does the gravitational force act? So the gravitational force will act from the center of mass. Really, it acts everywhere, but we can act as though it acts on the center of mass. And that's going to give some force. So that's going to be, we're going to label that Fg. And then there's going to be a buoyant force. So that's actually going to act from the middle of where the rod is, of the portion of the rod that is underwater. And so that's going to act upward. That's going to be Fb. And also, there's a force from the pivot. So I'll call that Fp. Now, ultimately, Fp is not going to affect the torque about the pivot point. We'll just need Fb and Fg for that. So where are these forces acting from? So the distance from Fg to the pivot point, or the horizontal distance, is L over 2, because it acts from the center, and it's a uniform rod. And Fb, well, the part of the rod that's underwater is 1 minus F times L. And of course, this quantity, and now the distance from the point where the rod touches the water, the surface of the water, to the center of the portion of the rod that's under the water is just half of the remaining amount. And so you can calculate that this distance, so let me just draw it down here, that will be 1 plus F over 2 times L. You can also see that because this point is actually the average of these 2 points. So now, what is the torque? And the torque from Fb and Fg clearly point in opposite directions, and so they need to balance each other out. So the torque from the buoyant force has to equal the torque from the gravitational force in magnitude. And so the torque from the buoyant force is the buoyant force multiplied by 1 plus F over 2 times L, and that equals the gravitational force multiplied by L over 2. L and 2 cancel out, so as I promised, L cancels out. Now, what is the buoyant force? Well, the buoyant force, by Archimedes' principle, is the weight of the displaced fluid. Well, let's suppose that the mass of the rod is m. Well, then the weight of the displaced fluid, or the mass of the displaced fluid, is going to be the density of water relative to the density of the rod multiplied by the volume that is displaced. So what we see is that the density of the water is actually 9/5 of the density of the rod, because the density of the rod is 5/9 the density of the water. Then we need to multiply by the amount of the rod that is underwater, because that is the mass of the displaced water will be 9/5 times the mass of the rod that is submerged, or of the part of the rod that's submerged. But the part of the rod that's submerged has mass m times the fraction that is submerged, and that will be 1 minus f. And then, of course, times g to get the weight. And so now we see 9/5 m, 1 minus f, g, and then notice that there's this factor of 1 plus f, equals mg. Naturally, m and g cancel out. And now, multiplying both sides by 5/9, we get 1 minus f squared equals 5/9. And since f is greater than 0, we can see that f squared is 4/9, and so f is 2/3. And it may be worthwhile to just do a quick check to make sure this is right. So if 2/3 of the rod is above the water, then the gravitational force, then the buoyant force will act at the 5/6 point, and so it will be, you'll get 5/6 and then times 9/5, and then multiplied by 1/3, because only 1/3 of the rod will be underwater, and that will indeed properly match the torque provided by the gravitational force if you do the calculations. So we can go back here and see that 2/3 of the rod is underwater. That's the closest to 0.67. And so this is the correct answer. All right, I hope that was helpful, and thank you for watching.